Welcome back to part 2 of this talk about Asian solutions to the curve shortening flow. Let me first recall the basic definition and the theorem that we are going to prove today in this seminar. So the curve shortening flow is a family of curves, gamma t, where t is inside some time interval j, such that the time derivative of this family is given by the curvature vector k, and the solution is called Asian if j, the domain of definition, is defined from negative infinity to t log, where t log is some numbers smaller than or equals to infinity. So the theorem that we introduced in part 1 and we're going to prove in part 2 is the following. So we'll show that there's an infinite family of compact Asian solutions to the curve shortening flow such that the union of the convex tau of the solution equals to h, which is the upper half plane. I will first briefly talk about the main idea in the proof. In order to construct new solutions, right now it seems that the only way we know is to glue grid rippers. So we're going to glue several grid rippers along the common asymptotes. So this is what first introduced by Engelnett and Yu recently in 2018. And this is one example where you have 4 grid rippers glued together. It becomes compact Asian solutions. But as you can see in this construction, there's some sort of a dilemma in this situation, because in the construction, if we use only finitely many grid rippers, then because of how we glue it, we have to glue it along the common asymptotes. So if you use only finitely many, they just stay in a strip. They are not going to span the whole upper half plane. But on the other hand, if you do it using infinitely many grid rippers, you ran into another problem because now the solution is non-compact. So in order to deal with this one, we have to be a little bit careful in doing the gluing process. So in particular, we are going to glue the grid rippers, but we are not going to do that at the same time. So that means we have to choose a sequence of time, Tn, which is a decreasing sequence of time, which tends to negative infinity, such that at around the time Tn, we glue a new grid rippers into your solution. If you put it another way, that means at the time capital Tn, some grid rippers in your solution has to disappear, has to die out. And this is one picture that roughly illustrates what is happening. So you will see that there's a figure 8 in this figure, and the figure 8 is modeled by gluing of 4 grid rippers. So this figure 8 will become smaller and smaller, and the construction that we want to do is that this figure 8 will unlock itself after some time and then disappear at this capital time Tn. So in particular, instead of constructing that Asian solution immediately, we will instead construct a sequence of solutions. These are essentially constructed already by Engelnett and Yu. So these Asian solutions has the following properties. So this Cn, first of all, start with n equals 0. C0 is just the Engelnett oval. And C1 is more or less formed by gluing a figure 8 to C0. Okay, and we do it inductively at a sequence of time. So what we get at the end is the following. So when t is very small when compared to Tn, it's much smaller than capital Tn, then the Asian solution Cn of t is just the previous one together with a figure 8. Okay, and then at the time around capital Tn, that new figure 8 disappear, and we allow it to flow for another very long time, so that when t is much larger than capital Tn, then Cn of t is just very close to Cn minus 1 of t. Okay, once we have constructed this sequence of Asian solutions, then we'll take the limits, and the Asian solution that we want to construct in the theorem is actually the limit of this sequence of Asian solutions. So this is a little bit abstract, but let me just show you some picture, at least about the first two of the whole sequence. So the red one is the C0, which is the angular TOEFL, and the blue one is C1. Okay, the next one. So as you can see, when, first of all, from top to bottom, when t is much smaller than capital T1, then the blue solution is more or less the red one, but there's a figure 8 glued to it. And around the time capital T1, that figure 8 disappear, and then we let it flow for a very long time, so that when t is much larger than capital T1, those solutions are close to each other. Okay, so this is the first picture. In order to visualize the other one, then you have to glue another figure 8 to C1 in a much earlier time, capital T2, and then so on and so forth. Okay. So now we're gonna tell you how this sequence of Asian solutions are constructed. We have to do it in a very controlled manner in order that we can take the limits at the end. So that will be a sequence of intervals for any t between negative infinity and capital T log. I will have a sequence of intervals, and then I will have a sequence of functions defined on this sequence of intervals, Gn. This sequence of functions has some properties, so it maps the endpoints to 0, and also it is monotonic. Once we have this sequence, we'll use that to define Cn by reflection. Okay, so we'll define Cn to be two parts. The first part is just the graph of Gn, okay, and the other part is the graph of negative Gn. So basically, we're taking one part of the graph and then reflect this along the y-axis, and then glue them together along the endpoints. So that's why we require that the Gn sends the endpoints to 0. This is how we glue them together along the y-axis. So this is the first three functions, G0, G1, and G2. G0 is just half of the angular TOEFL, and G1 we have a little bit more. We have a part that is close to the angular G0, and then there's another part which, when reflected, becomes a figure 8. The same for G2, just that G2 has yet another figure 8 on top of G1. Okay, so from this picture, from the function Gn's, you see that they are disjoint from each other, but you're reminded that the closed curve is not exactly Gn. Gn is just one half of Cn, so we have to reflect all these G0, G1, and G2, and then we glue them along their respective endpoints. So all these Cn, Cms, they are gonna intersect each other, although the corresponding function Gn do not intersect each other. So this is one curious observation where in the arguments we have to use maximum principle, but we have to use it in a very careful way, because sometimes we're actually using it on the functions Gn instead of the curve Cn. Okay, so well, now I have to tell you how to construct this Gn. This is the smoothing method by the Engelert and Yu. So before like constructing this Gn, they have to first construct this broken solution, which I call G bar of n. G bar of n is formed by Goulding grid rippers. Okay, so we take a copy of n plus 1 grid rippers that is moving to the left, and then we take another n grid rippers that is moving to the right, okay, which I denote as G0, G1 up to Gn plus for those who are moving to the left, and for those who are moving to the right, we denote that using the minus sign. Okay, so we have to glue that alternatively. Okay, and also we choose the width of this G minus K and G plus K to be the same, which is equals to this number, AK inverse. We'll talk about the AK inverse later on. Okay, so let me show you the picture of the broken solution. So this is the picture of the broken solution when n is 1. As you can see, there will be 2 grid rippers moving to the left and 1 moving to the right, and then we glue them like alternatively. The gluing around this y-axis is, in this case, I'm just using the straight line to join them together. Okay, it's not really too important how we're going to glue that. Okay, the point is that there's a smoothing process introduced by Engelert and Yu, that after smoothing, this in this picture, G bar of 1 becomes a G of 1. Okay, so G of 1 will look like the grid rippers on the tip regions, but it's smooth along the y-axis. And in particular, they forms this right angle at the end point, so that when you reflect this G1, you glue this to become a smooth immersion. Okay, so well, let's go back a little bit. Let's go back to this picture. So the Asian solution that we want to construct will be a sequence of Cn. It will be a limit of a sequence of Asian solutions, and the sequence of Asian solution Cn is constructed by this function Gn. And this Gn is just a sequence of increasing function. So at the end of the day, we're going to take the limit of this Gn. So this is a sequence of increasing function, and then we're going to take the limits. Okay. Of course, in order to take the limits, you have to have some good estimate in order to do that. Okay, the monotonicity is good. We're going to use that soon, but we have to be more specific. So in order to take limits, we have to control the area actually between them. Okay, but before we do that, let me say a little bit about the grid rippers or the figure H that is glued in the process. Okay, so in this picture we have this illustration which tells you that in order to glue a figure H and let that figure H disappear, we have to really be careful about when choosing the area bounded by those two loops in the figure 8. Okay, so in the left picture, this is the situation that we want. We want the top loop to be much larger than the bottom one, so that when you apply this curve shortening flow, the smaller loop will disappear before the bigger one, so that we have the picture that we want. On the other hand, if you use the right one, then you got into trouble. So this is the case where the top loop is not big enough. Actually, it's smaller than the bottom one. In that case, when you apply the curve shortening flow, the top closed loop will disappear before the second one. And in that case, you actually encounter singularities. Okay, if you encounter singularities, then of course you cannot continue the flow at least smoothly. Okay, and this is the situation that we want to avoid. Okay, so that's why in the previous picture, let's show you this picture. You'll see that the figure 8 at the top has that property, that the area on top of the loop on top is bigger than the one at the bottom. So this is something that we have. We need to impose in order to make the whole argument works. Okay, but on the other hand, this is actually posing a technical difficulty because of the following. So this area, which I call the error, which is more or less, roughly speaking, the difference between A1 and A2, I call this the error. This error actually will not go away, will stay there forever. This is a property of curve shortening flow. So this is a theorem that is known for a very, very long time, as long as the start of curve shortening flow. So if we have a closed curve, and let the area be the area bounded by gamma t. In case when gamma t is not embedded, then we have to take the sig area. So if that's the case, then if you take the time derivative of this area function, then it's going to be constant, and which is given by negative 2k pi. K is just the turning number of your curve. If we go back to our family of solution here, then you see that they all have turning numbers equal 1. Okay, so in particular, the sequence of Asian solutions, those CNs, they all have the same turning number. So that means the area bound between one from the other is actually constant. Okay, because they are subtracting the area. Okay, and k is the same for all n. Okay, so this error, the area bounded between those two functions, gn and gn minus 1, they will stay there forever. They are not going away. Okay, so this is one illustration. So on top we have G0, G1 and G2 represented by the red, blue and purple curve. Okay, and let's say when we apply the curve shortening flow, let's say all the figure 8s disappear. Okay, even if that's the case, E1 and E2, which is the area bounded between G1, G2 and G2, G3 respectively, they will stay there. Okay, so these are just the first two errors, but as you can imagine, because we have a sequence of GNs, and then the GN will gives you a sequence of error, G1 up to Gn. Okay, and we have to add them together from this graphical representation. So which means that this error, in order to get at least a C0 estimate, we'll at least assume that the error is summable. Okay, so that means on one hand I need to have the error in order to avoid singularity. On the other hand, this error has to be controlled. It cannot be too big. Okay, so to control the error, actually this is related to how we choose this width of the figure 8. Okay, so we call that we have a sequence of number an, where an inverse is the width of the nth figure 8 that you glue to to in the process. Okay, so the second point is that there's actually a key observation is that I can choose this G1 up to Gn in a scale invariant way, so that I can control the error En, which is roughly equals to An to the power -2. Okay. On the other hand, because this An inverse is the width of the figure 8, we also need that when you sum all this An inverse, we'll take the summation. It has to be infinite because we want to construct the Asian solution when it's spanning the whole upper half plane. So I need this number, I need the sum of the width to be infinite. Okay, and that means that is telling us the choice of the sequence. Okay, so I will have to choose An to be some sequence which has such that is summable. It's not summable, but is square summable. Okay, one of the examples, of course, we all know is the harmonic sequence where An's equal n. Okay, this is how we control the area. Okay, by choosing this sequence in the correct way. Okay, I'm not going to go into lots of details about how to do the estimate, but at least I want to show you one lemma before I end this part 2, how we're gonna use this area estimate to come up with, for example, the C0 estimate. Okay, so this is what I call the C0 estimate at the tip region. By the tip region, I mean the region that is screwed using the grid ripples. Okay, as opposed to the middle region which is close to the y-axis. Okay, so let's this GT be the grid ripples, and let CT be any curve shortening flow which is lying in a strip that is a little bit bigger than those containing the grid ripples. Okay, but this CT is outside of the grid ripples. Okay, and also let's say we know the bound between of the area between CT and GT, and let's say we know that it has a uniform bound which is A. Okay, then the following holds. Then there's a T log, positive time T log, and a positive number C, depending only on the area bound A, so that when the curve shortening flow is a flow long enough. Okay, so that means when capital T is bigger than this capital T log, then the distance between the tips of the curve shortening flow CT and the grid ripple is smaller than C. Okay, that means we sort of have a C0 estimate. So the curve shortening flow CT cannot be too far away from the grid ripples once you allow the flow to flow a long enough time, and once you has the area bound between those two solutions. Okay, so I'll just use this picture to describe how the proof goes. So this is an illustration of the situation where you have the grid ripple GT, and then the red line is your solution CT. And we know that they're all lying inside this strip region. Okay, and the area between the two is bounded by A. Okay, so now take a look at this rectangular region which I call B. Okay, so this region is the region where your graph C can always be written as your curve shortening flow C can always be written as the graph of two functions. Okay, so this is a fixed rectangle B, and inside that you have graphical representation, and that's and this is the region where we can apply the famous Eckhart-Hurston interior estimate. So if you let time to be large enough, then what I can attain by this interior estimate is that uh, it can be as strict as I like. Those two graphs can be as close as I like to a straight line. Okay, and of course that means if both are very, very close to a straight line, then the area bounded by those two straight lines cannot be small. Okay, so that means the width, okay, put it another way, that means the width of this rectangular box B cannot be arbitrarily long, because if this is the width of this one is very, very long, then the area bounded between CT and GT will be eventually bigger than A. Okay, so this is like one examples of some CCO estimate that we can do once we have the area estimate. Okay, so this is just one estimate that we control the tip region, and let me just say that we'll still have to do something about controlling the curvature when this untangling occurs at the time capital Tn. But I think I would just skip that, and that is the end of my presentation, and thank you.